Hello. This lecture will cover pages 73 through 76 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Operational Amplifiers, Chapter 4E, the Non Inverting Amplifier. The previous two lectures we talked about the buffer amplifier or the unity gain amplifier and the inverting amplifier, and now the third configuration is the non-inverting amplifier. This is what the non-inverting amplifier circuit looks like. Notice that the input voltage Vs feeds into the non-inverting input. The feedback resistor feeds back to the inverting input, and we have another resistor from the inverting input that goes to ground. There's no virtual ground in the non-inverting amplifier circuit. It's only found in the inverting amplifier circuit. Now, we're going to analyze this circuit, but before we do, I want to point something out to you. I'm going to draw two circuits here. I'm going to draw two non-inverting circuits. One is going to look like this. And here's my Vs coming in. I'll just do it this way. And I'm going to show my minus input here, and I'm going to come around here, and I'm going to show you a resistor here. And I'm going to show you a resistor here, and I'm going to take that to ground, and I'm going to call this here V out. That clearly is a non-inverting amplifier circuit because the input voltage feeds into the non-inverting input. That's how you tell it. I'm going to redraw that circuit, and I'm going to redraw it to look like this, where this is V out. Here's my Vs coming in. It's a non-inverting amplifier circuit, and I'm going to draw the circuit like this. This I'm going to call R2, this I'm going to call R1, this I'm going to call R2, and this I'm going to call R1. I want you to look at those two circuits. They are both non-inverting amplifier circuits, and they are identical circuits. Look at it long enough to understand that these circuits are identical. They're just drawn differently. Take this circuit here and rotate, take this point and just pull it back to here. Take this point and pull it back to here. It moves this resistor up here, and this resistor comes along for the ride. Or take this point and stretch it over to here. Take all this and just stretch it all over to this point and bring that resistor down. These are exactly the same circuits. Don't let that confuse you when you see that in homework or on an exam. They are non-inverting amplifier circuits, and they're identical. Okay, let's take a look at analyzing this circuit. What we're going to do here is we're going to use a procedure of basically taking this Vs input, this Vs source, and we're going to project it over from the plus input to the minus input. I mean, that's what operational amplifiers do. Basically, they work to keep these voltages identical. I told you we could look at it another way. We have an infinite input resistance, and with no current flowing, if there's Vs here and there's no current flowing through that resistor, there's no drop, so we have Vs over here. So I'm putting Vs at this point right here. This Vs gets projected to here, and that's the same point as here. I labeled this current I2 plus the minus. I labeled this current here I minus, and I labeled this current I1 plus the minus. By Kirchhoff's current law at node 1 using nodal analysis. Since V plus is approximately equal to V minus is equal to Vs. So whatever that voltage is there in our problems, you can just put it down there. I get a plus I2, minus I minus I1 equals 0. This goes to 0 for the reasons we discussed. I calculate I2. What's I2 here? It's this voltage minus that voltage divided by R2, minus What's this current I1? It's this voltage here minus the voltage here. It's Vs minus 0 divided by R1, but I just write it as Vs over R1. I just use a little bit of algebra down here. Isolate the variable, isolate Vs. I end up with the V out over R2 is equal to Vs times this quantity here. And if you form the ratio of V out over Vs, by definition, that's our closed loop gain. The gain of this circuit is R2 plus R1 over R1, or R1 plus R2 over R1. If you will, that's 1 plus R2 over R1. The gain of the non-inverting amplifier configuration is always 1 plus R2 over R1. That's very important. If you recognize this, if you recognize it's a non-inverting amplifier. Two things I want you to take from this. The non-inverting amplifier circuit always has a positive gain. It can never be negative. You're always going to get a positive multiplier of this voltage to the output. And number two, it always has to be greater or equal to 1. You're never going to get a voltage gain less than 1. It's always 1 plus something. And if you want to get exactly 1, R2 has to be 0. And if you make R2 0, that's a wire from there to there, which is back to the unity gain amplifier. This has no play in the circuit when you do the analysis. If the R2 is 0, you get a unity gain amplifier. That's the first configuration we talked about. So there's the equation that I want you to use and a non-inverting amplifier for a non-inverting amplifier configuration. You can use equations A and B, our control theory equations, and that's what I've done here to show you how you can analyze it. It's real easy to analyze. Just basically look at this circuit here, and I want you to realize that it's C times G divided by 1 plus GH, okay, where C is equal to 1. Why C equal to 1? Because there's nothing in front of it here. You have Vs here and you have Vs here, so this C is Vs over Vs, which is a 1. So if you want to draw this C in as a 1 in a block diagram format, that's why I'm getting C is equal to 1. So the closed loop voltage gain of this circuit is simply equal to G. We know what G is. It's the open loop gain. It's the open loop gain. Forget about all the feedback. It's the open loop gain of this, and ideally we treat that as infinity. That's going to be infinity. So there's your A open loop divided by 1 plus GH, G's equal loop. And what is H? What percentage of this voltage here are you feeding back? Look at this. What percentage of that voltage here are you feeding back at that point? Well, it's just R1 over R1 plus R2. It's a voltage divider rule. This is ground reference here. So the multiplying factor to transform this voltage to this point is R1 over R1 plus R2. 1 plus this quantity is just forget about this. Complex fraction, rotate it and bring it up. AOL cancels. And there's your closed loop voltage gain, 1 plus R2 over R1. Using control system theory equations, you get exactly the same thing if you work through this analysis. On page number 75, let's take a look at analyzing the non-operational amplifier circuit shown here. Non-inverting operational amplifier circuit. Well, we take a look at this, and right away we know that it's a non-inverting amplifier because the input voltage feeds into the plus input. Well, in this case right here, you can go, they want you to find the closed loop voltage gain in decibels, then find the output voltage for this circuit. You could write a nodal analysis here if you want to. You could project this voltage here of 100 millivolts to this point here, to that point, and assign some currents, and you could solve for the gain. V out over Vs, just form the ratio. But why do that whenever we've already done it? I'll allow you to go straight to that equation. If you recognize this as a non-inverting amplifier circuit, you can say that the gain is 1 plus the ratio of this feedback resistor over that resistor. Don't get them mixed up. 30K over 5K is 6, and you add 1 to it, the gain's plus 7. We know it's always a plus 7. dB is 20 times the log of the absolute value of plus 7. You get 16.9 decibels. The closed loop gain, by definition, is V out over Vs, which is plus 7. So if you know Vs, which is 100 millivolts, you could be able to solve for V out. It's a multiplication. It's 700 millivolts. You have 100 millivolts in, you get 700 millivolts out. Let me add a little dimension to this, though. If the value of R1 up here is changed to a 1K ohm resistor, and Vs represents the peak of a sine wave. Remember, we did this before. Let's pretend that's just the peak of a sine wave. In other words, we have a sinusoidal waveform. It's gone up like this, and it's gone down. Okay, and it's at 0 volts, and it goes up to a plus 100 millivolts peak, millivolts, tenth of a volt, and it goes down here to a minus 100 millivolts. That represents a peak, but we're going to change this R1 to 1K. Will the operational amplifier saturate? Will this saturate? And I'm giving you the rails of plus 10 and minus 10. Well, no, it won't. It won't saturate. Now, why won't it saturate? Well, should be your logic. If this is a 1K resistor, the gain of this circuit is 1 plus 30K over 1K. That's 1 plus 30. That's the gain of 31. And if you take 100 millivolts times 31, you get 3,100 millivolts. You get 3,100 millivolts. Well, we know that's 3.1 volts. So it's going to go to a 3.1 volt, and it's going to go to minus 3.1 volt. You're nowhere near the rails of plus 10 and minus 10. So it will not saturate. But remember the example I gave you in the previous lecture. There is a point at which you can change that resistance value low enough that you're going to drive it to that point on the positive and that point on the negative. At that point, you hit saturation and you get distortion. And instead of your outputs looking real nice and clean, instead of your output waveforms looking real nice and clean, if the rail, if it's trying to get to 18 volts and minus 18 volts, that's where it's trying to get to, and your rails are only plus 15 and minus 15, that's where your rails are at, right there. Your specs are going to tell you that you're only going to get to within 1.5 volts of the rail with our operational amplifiers. So it's only going to get to 13.5 and minus 13.5. So what you're going to get is a waveform that looks like this. That ain't going to be there. That ain't going to be there. It's going to distort and it's going to saturate. And that's no good when you hit saturation. Saturation was only good when you're in digital circuits. You want transistors to saturate. You want them full on to get a 0 or a 1 logic level. In analog circuits like this, saturation is bad news. So that took us through page number 70. What was that? That was 75. And page 76 is where our next lecture is going to take us. And I just want to mention something to you. We'll begin our next lecture here, but it's so important I have to mention it in the final minute. If you can identify an op-amp circuit as one of the three simple configurations that we discussed in the previous lectures, just use the gain equations as shown. Just use the gain equations, a gain of 1, or a gain of minus R2 over R1, or a gain of plus 1 plus R2 over R1. Just use them. Saves you a lot of time. But if the circuit becomes more complex, and you're going to have some of those circuits in the next, lecture, you have to use a procedure. This procedure is not in the book. It's a procedure that I've come up with, and it's a real simple 3-step procedure. If you understand this procedure, I've had all my students call me, most of them, and say, look, I'm working on type of problems other people have problems with because they don't use this procedure. So get to know this procedure. I've used it a couple times in previous problems in this last lecture and the lecture before that. But you're going to get to know it pretty well coming up because we're going to work these problems in the next lecture. And that concludes this lecture.